Today we are beginning our new unit in logarithms. Now, logarithms are very intimately tied to another type of function that you studied very in depth in grade 11. Because we are short on time, there's no place for me to really do a full rundown of exponentials, but I assume that you are familiar with the basic properties of exponents, which I'm just going to state here, and then I'm going to assume from now on that you know them. Now, I did mention these in my grade 11 review video, but just to recap, suppose I have numbers a, b, and c, all non-zero. I have that a to the b times a to the c is equal to a to the b plus c. A to the b divided by a to the c is equal to a to the b minus c. Then I also have that a to the b, all of that to the c is equal to a to the bc. Okay? Those are the core exponential rules. Now there are some other identities which you should be very familiar with, namely that a to the power of 1 over n, where n is just some number, I'll let n be another number non-zero, is the same thing as the nth root of a. And what this is asking for is the number such that the number to the power of n is equal to a. Okay? Sometimes this thing can be a little confusing, so just be really sure that you get this relationship down in your head. The other property which is implied by this is that a to the negative 1 is equal to 1 over a. Right? Okay, those are the main properties of exponents that we are going to be using throughout this entire lecture. With that groundwork being done, we need to now start thinking about the more general relationship of exponents. Namely, if I have that a to the x is equal to y, where a, x, and y are all numbers, what does that tell me about a, x, and y? Right? So, just again to recap, roughly speaking, what you can interpret exponents as is that if you multiply a by itself x times, right, that's the same thing as a to the x, right? With the case of fractions and negative exponents, it becomes a little trickier, right? This is not so much of a good explanation anymore of what's going on. In fact, we have to consider exponentiation its own sort of operation. It's similar to how with division, right? We usually, like if you get a number like 4 and you divide it by 2, right? It's easy to think about that because you think about division in terms of sharing, right? You get like 4 balls and you divide them between 2 people, and the division just counts how many balls each person is going to get. But when this becomes a little trickier, like let's say I put like a square root of 3 in here, then that interpretation doesn't really make any sense. Firstly, like there isn't a square root 3 number of people here, and secondly, like how do you even interpret that result, right? So in a similar way, we have to shift our focus of exponentiation into a more abstract setting. It's no longer simply just multiplying a x times by itself to give you y, although that is what informs our intuition for this operation. Okay? Excellent. So, that being said, let's go and consider something that looks completely different. We're going to talk about powers of 10. Powers of 10. Okay. And now what I want you to think about is what is 10 to the 1, 10 to the 2, 10 to the 3. And similarly 10 to the 0, negative 2, and negative 3. Okay? So you should get that this is 1,000. This is 100. This is 10. 0. 1. Remember that one. I'm going to write in fraction form. Right? So these are the numbers. Okay? Let's just plot these on a graph. Okay? And this should look very familiar to you. This comes directly from what you know in exponentials already. So this roughly, it looks like that. And then the graph just goes way up. right, I can't even draw 1,000 on this graph, right? So roughly, if I just connect all of these, it looks like that. Okay, and this illustrates the general pattern that exponentials have, which is that they cross the y-axis at x equals 0, y equals 1, right? That's their y-intercept. They have no x-intercept. This is a horizontal asymptote, as we have seen before. And this horizontal asymptote occurs at y equals 0. It's a straight horizontal line that the function will never touch. Okay? And you can see that just by looking and extrapolating what happens here, right? You're always going to get very, very small fractions, but they're never going to be 0. Right? Okay. So now what I want to do is I want to recall what we discussed earlier. We discussed earlier in the very beginning of the course a concept called inverse functions. Okay? So just visually, I want to think about what the inverse of this function will look like. Okay? So let me just draw in a highlight color, maybe orange, this exponential function. Okay? And this, let's say, is 10 y equals, or f of x equals 10 to the x. I want you to draw me the inverse function of 10 to the x. Use your paper, just try and graph it. And hopefully, what you got, remember the inverse function can be graphically interpreted as a reflection about the line y equals x. If you just look at it symmetrically, we get this. Right? This yields a symmetric picture for this graph. Okay. One thing that is sort of created organically from this reflection is a vertical asymptote. A vertical asymptote, so this is again f inverse of x. Now we get a vertical asymptote at x equals 0. Okay? That's not something that this had, but it got created because when you do this reflection, this asymptote here, right, if you reflect it in this line y equals x, becomes this line x equals 0 here. Okay, so to recap, here we have a horizontal asymptote. When we took the inverse, it became a vertical asymptote. Here we got very large end behavior, and here that end behavior sort of seems to plateau out, but it's still increasing. It's just getting flatter and flatter. Okay. Excellent. So this here is the inverse of the exponential function, and this thing is precisely the object of study here. Right? We call the inverse of an exponential function is the logarithm. More precisely, the logarithmic function. Okay. Now, we should focus a little bit on evaluation now, because it's great that we have this graphical interpretation of what the logarithm should look like, and we understand that it is the inverse. However, that doesn't tell us how to evaluate it or how even to write it. So let me go ahead and give you the strict rundown of how we have to interpret the logarithm. Again, we'll keep using our powers of 10. Maybe we'll just use 10 to the 3. And in general, we're considering the problem, remember, 10 to the x equals y. And remember, when we were taking inverses, what we are actually doing is we are switching x and y around and then solving for y. Now, I hope you see a problem here. I hope you see a very big problem. How are you supposed to solve for y when y is in the exponent? That's a very difficult question to answer, right? In fact, it's so difficult that we have to create an entirely new operation in order to be able to get this y out of there, right? So for now, let's just call this the log operation. Okay? So what log does in our heads, what we should think is log will bring down y. So in other words, log 10 of y should be equal to just y. Okay, that's what we want log to do. Right? So because we did it to one side, we have to do it to the other side. Okay. So this is what we haven't really defined strictly what log will do. All we know is that it will bring down y. Okay? It will just kill everything and get us back y. Okay? That's what we really want log to do. And then we get this weird relation, y is equal to log x. And therefore you see that f inverse of x is just, log of x. That's it. Right? But, so everything that we did here was fine, except that we don't really know what this operation log is doing. Okay? All we know is that it is somehow the inverse operation of exponentiation, that if you apply log to this thing here, it will give you back the thing in the exponent. Maybe we should write that down. If we apply log to, so log is a function, okay? So if we apply the function log of x to 10 to the y, we get y. Okay? In other words, it pulls out the exponent and then just kills the 10. Okay? So the answer is the exponent. Okay? Excellent. So this is what logs are really all about. They are about analyzing exponential relations like this and turning them into a more neat form by applying this log function. Now, as you can see here, we had to apply the log function to get rid of the 10. What happens if this was not 10 anymore? What happens if it was just 2? Okay? What happens if it was just 2? Then, we would still have to apply some sort of log function. However, it would not be the same log function as we did here. So maybe we'll call it something. We'll call it, log 2. Log 2. We'll put a 2 in the bottom just to tell us that what this function does, it will bring down y, but not from 10 to the y, it will just kill 2, right? So the bottom tells you what it kills. Okay? And because these two match, it sort of removes it, and then you just get y is equal to log 2x. Okay? So, and now, we're going to continue this pattern. If we apply log 2 to 2 to the y, we get y. And again, the answer is the exponent. Okay. Now hopefully you can see how to generalize this. In general, we are given this situation, so let me just write down the general case now. In general, we have a relation 2 to b to the x is equal to y. This is an exponential function. Right? Okay. We can also, what we want to do is we want to be able to find the inverse, right? So to find inverse function, what we need to do is we need to switch the x and y and then solve for y. Okay? Excellent. So what we're going to do then is we are going to do log with a little b at the bottom, and the little b just tells us that what this log function does is that it kills the b and just gives us y. Okay? So if we do this to both sides, we'll get this, right? And then we just get y is equal to log bx. And this is what we define to be the inverse function of the exponential, right? This was the exponential function, and this is its inverse, right? This here is the actual formula for the inverse, okay? Okay. So now that we've gone through the notation, let's go really in depth into this log thing and see exactly what it does to numbers. In particular, I want to just evaluate log for a bunch of numbers and then see if I can come up with any general patterns. To do this, we'll just go back to log with base 10. Okay? Maybe I'll put a 10 in the bottom here, just to be super clear what we're doing. Alright, so I'm going to keep that little bit of help right up there. Let's just see. So log, so for example, log base 10 of, I don't know, pick a number. Let's just try like 1,000. Okay? Well, we know that 1,000 is equal to 10 to the 3. So log 10. Right? But remember what log 10 does? It kills the 10 and it brings us 3. So this is just 3. So log base 10 of 1,000 is going to give us 3. Right? Just for like communication purposes, we say this expression, we say log base 10 of 1,000. Right? So this is the name of the function. Right? The function's name is log base 10. Okay? And then we want to say we want to do log base 10 to 1,000. Right? I know the wording's a little weird, but it's just something you have to get used to because it's standard notation for everyone. Right? So we were able to figure out what happens when you get 1,000. Let's try another easy number. Let's try 1 over 100. Try that yourself. Hopefully you realize that log base 10 of 1 over 100 is the same thing as 10 to the negative 2. And therefore we're just going to get back negative 2. Okay. Now I want to try a more hairy number. And I want to try maybe, let's say, just 5. How are we going to do that? Right, that's not very easy to do. And the reason why it's not very easy to do is because we don't know. We have to ask ourselves the question, what number do I raise 10 to get 5? Right? We are trying to solve then in our heads 10 to the what equals 5. Right? That's the question that we were able to solve for the previous 2 examples, but we cannot solve for this one. If we did have a number here, then we would be able to just put that here. We could just write log base 10 of 10 to the whatever that special number is, and then our answer would just be x. Okay? But we can't do that. It's definitely not easy, which is why what we're going to do is look back here. Okay? The answers are all here. We are trying to solve the equation 10 to the x equals 5. Visually speaking, what that means, okay, we've gone through this idea plenty of times throughout this course. Whenever you're given an equation of this form, what you're graphically asking for is when does the function 10 to the x intersect the line, the horizontal line, y equals 5. So let me draw y equals 5 here. It's like a line that goes like this, right? And remember, this is our exponential. Now to do this, you could use Desmos, you could use any variety of tools. However, there's a really handy button on your calculator. So let me just write that down. We're going to shortcut all this work, by the way. We're going to just, this is what we need to solve, right? X is our answer. Remember, the answer is the exponent. When you're doing logs, this little piece of wisdom will guide you every single time. The answer is the exponent. Okay? So what you can do on your calculator right? So what you're going to do is you're going to press the log button, log, and then you should get an input that looks like log of a number, and then you just put in 10, put in 5, right? So you'll get that, and then you'll just evaluate that. Okay. So for me, that gives me 0.6989 roughly. Okay. Now the reason why this thing doesn't have a subscript like we did over here is because by convention, we'll just write that here. A little bit of a warning for you. Okay. It's a little confusing, I know. By convention, log of x is the same thing as log base 10 of x. So basically 10 is the basic logarithmic base, right? If you have to take log of another number, right, then you change the number here, and then this does not apply anymore. But just in general, when you just have log, right, that typically means log base 10. All right. So really, if the calculator were super accurate, it would put a 10 in the bottom there. All right. So this is how you evaluate the 10 log with your calculator. Right? And now remember what this is saying, right? Remember what this result is, why we were getting this result. This result tells us 10 to the 0.6989 is equal to 5. Remember, the answer is the exponent. So in this relation, what you can do is you can just verify that 10 to the 0.6989 is roughly equal to 5. I'm getting 4.999. Right? And therefore, we can substitute this into 5. So log base 10 of 10 to the 0.6989, haven't changed anything in the question, you just get 0.6989. I hope you really see now that the best way to understand logarithms is just to think about this. The answer is the exponent. When you're writing this relationship in exponential form, 10 to the x equals 5, right? The answer x is the answer, the exponent x is the answer to the logarithm question. Alright, we are ready to tackle this in its full generality. So, just by paralleling this example here, remember the question that we're trying to answer is, what does log base b of x mean? Okay, y equals log base b of x. That was the function that we kept getting in the previous examples, and now we're trying to evaluate it, right? Well, as we've seen here, it just means this. In other words, b to the y is equal to x. Okay, the answer y is the exponent. Alright, b here, the little b in the bottom, is the base. This is all you needed to know. Okay? If you did not understand any of that, this is all you could have gone off by. Right? This is what we've been building up to. With this, we can actually start doing some pretty complex things with logarithms. We're going to tackle those now. So I'm going to put a couple of problems on the board, and I want you to try and solve each of them using that last insight that we had up here in the upper right corner. So, for example, what happens if I say log 2 of 8? Okay, so I want you to be able to answer something like that. Or, what about log 4, 2? So some simple examples to get us going. Okay. So this one here, hopefully you recognize that 2 to the 3 is equal to 8. And again, the answer is the exponent. So this thing is equal to 3. Here what you're thinking of is, again, 2 to the what equals 4, right? And in this case, I think sorry, no, it's the other way around. 4 to the what equals 2. 4 to the what equals 2. And, sorry, this should not be a 0. It's 1/2, right? Because square root of 4 is equal to 2. So here it's 1/2. Right. That one's a little tricky. Here, remember log without any number at the bottom just indicates log base 10. So you're thinking about what number do I raise 10 to in order to get 10,000. Okay. And here it's 4. So the answer is 4. This one, I'm just going to go through them now. The answer is 4, the answer is 4, the answer is -2. Right? This one, the reason why is because 3 to the -2 is equal to 1/9. Again, the answer is the exponent. You may want to get into the habit of literally saying this out loud to yourself every single time you tackle a log question. The answer is the exponent. The answer is the exponent. All right. Excellent. So, hopefully we've gotten the hang of evaluating some simple logarithms. Now, using a calculator, you can evaluate any type of logarithm. That's the good news. So, log, for example, base 7 of 16. Okay. So what you do is on your calculator, you should get a button that looks like this: log, little box, bigger box. Right. This is the number that this is the box that you want to use, and then you just plug in. So you do log, put a 7 in the bottom, 16 in the top, and evaluate that. For example, in this case, I'm getting roughly 1.42. Okay? You will never be asked to evaluate an impossible logarithm without a calculator. You will be asked to evaluate certain logarithms without a calculator. Right? So make sure that you have that distinction. There are some problems where you will be forced to use a calculator. Humans are not very good in general at thinking about exponentials that involve very strange exponents. However, in the simple cases like the ones that I just gave you, you should be able to come up with an exponent that will give you the answer to this logarithm thing, right? So I really want to emphasize that the logarithm is not an operation, it is a function. The logarithm is a function, right? And recall what a function means. It has an input. I should maybe put log b. Takes a number and gives out a number, right? So with that being said, we want to consider a couple of very simple questions. Namely, what happens when I do this? Log bx plus log by, log b x minus log by, log b x to the y. So these are just simple things that will help us evaluate logarithms a little better. Right? These are known as the logarithm rules, or log laws. Right? And we're going to figure out what these things are, just by considering exactly what we were doing the other time. Right? So maybe I won't use x and y, maybe I'll use alpha and beta. Alpha, beta. Okay. Good. So, remember what this means, right? This means that b to some number equals alpha. The answer is the exponent, right? And we're going to take this number and add it to the number that you get if you just had b to the what number gives me beta, right? So two different answers, and what this expression means is that I'm just adding them together, right? So think about it, what does that mean if I have to add them together? It's a very strange thing to think about, but there's one little trick here that will make everything click. You see, these two are equations, right? black box and orange box, B, alpha, and beta. Okay? We can do something to them, very clever, which is to multiply them together. And what does that give us? B to the black box times B to the orange box is equal to alpha times beta. Now it should be clear. Okay? Because by our law of exponents, we get B to the black box plus orange box is equal to alpha beta. So in other words, what we can do is we can just rewrite. Remember, this expression here is what we were after, the black box plus orange box. Right. This thing here is log of B to the alpha plus log of B to the beta. This is exactly what we're after. Okay? And what this equation here tells us is that we can also interpret it a different way. We can interpret it as log to the base B of alpha times beta, which is equal to black box plus orange box. Black box plus orange box. Okay. Hopefully you see that it's just the simple rearrangement of this expression that gives us this again. And therefore we have an equivalence between this and this. So our derived log law is log to the base B of alpha beta. The quick way of remembering this, although I would not recommend it, is that you can, if you're adding logarithms, you can smush the alpha and the beta together and just multiply them. Okay? I would not recommend this because people always mix it up. Now, let me tell you what they mix it up with. They mix it up with this. Log B alpha log B beta. And they think that this is the same thing as log of alpha plus beta. Not true. This here is one of the biggest mistakes people make with logs. And it will be a great source of confusion for you when you are given problems that look like this and you try and do this and you wonder why you got the answer wrong. It's because you didn't actually use one of the log laws. This is the rule. This is not. Again, you have to add the two logs together, not add what's inside them. You add the two logs together and it gives you a multiplication on the inside. Okay? You cannot multiply two logs together and expect to get an addition on the outside. This is not a logarithm law. Okay? So let me just quickly go ahead and fill out the next one. This one will be left as an exercise to you in your homework eventually, or it will come up as a test question. So I want you to be able to derive, like I just did here, what this is. And it's not too much different. You just have to use another one of those log laws that, those exponential rules that we used before. Okay. So to figure out this thing, what we're actually going to use is this right up here. This law that we just derived, it gives us everything that we need to know to be able to solve this question. All right? So observe that if alpha is equal to beta, then this implies that log B alpha plus log B alpha is equal to log B alpha times alpha, which is the same thing as alpha squared. In a similar way, if I just add copies of this, so if I just multiply this by some number, beta, right? If I just multiply log B alpha a couple number of times, then I should get that same number of copies right up here in the exponent, right? And this is exactly what we were trying to do here. And so we've derived that beta log B of alpha is the same thing as log base B of alpha to the beta. The quick way of remembering this rule, you can pull out exponents. Now I want to take this rule and go back to what we were doing at the beginning, where we were canceling out. I want to make precise what I meant by killing the 10 and bringing down the exponent. Okay? And it goes like this. So remember how we were solving our logarithms earlier? We were saying, aha, well log, let's just do base 10, of 10 to the 5, right? Well, we remember what we were saying is this log 10 thing, it kills the 10 and gives us the 5. Well, now we can reinterpret this a little more rigorously using what we know about logarithms now. Right? So observe that we can apply this rule here, and it will look like this. 5 log 10 of 10. And let's ask ourselves what this thing is doing here. Well, this is asking what number do I have to raise 10 to in order to get 10? Well, no duh, it's 1. So, really all you're getting is 5 times 1, which is 5. That's really what was going on when I said we kill the 10 and bring down the 5. Okay. Alright, so now that everything there has been made clear, let's go and evaluate and figure out some basic properties of logarithms. We can infer most of these actually just from the graph. So, the very generic exponential function looks like this, right? And therefore, just by symmetry, the generic logarithm function looks like this. Okay? This one passes through the point 0, 1, and it has a horizontal asymptote at x equals 0. Sorry, y equals 0. Okay. Excellent. So, just thinking about it symmetrically, where in the reflection does this point get sent to? Just think about it for yourself. It gets sent to the point 1, 0. And that's just by symmetry across this line. Okay. What does this mean? What does this mean? Because every logarithm function sort of looks like this. Right? It doesn't matter if it's log base 2 of x, or log base 5 of x, or log of x. Okay? They all sort of have this generic shape of vertical asymptote and passes through 1, 0. Just like how every exponential function, b to the x, has this shape where it has a horizontal asymptote at y equals 0, and it passes through the point 0, 1. So all this means is that if I do log the base b of 1, that will always give me 0. And why is that? Because remember when we're evaluating this, we're thinking, what number do I have to raise b to in order to get 1? And it should be common knowledge by now that, you know, the number that you have to put up here is always going to be 0. So that is why we're getting this. Okay? The next thing that I want to consider is the domain and range of the log function. Okay? As we can see here, the exponential function clearly goes to infinity. We have, for any exponential function, the limit as x approaches infinity is equal to infinity. The same applies for the logarithm function. So limit as x approaches infinity of log b dx is equal to infinity. It just goes up and up and up. It does seem to plateau, but it never sort of like reaches a point where it doesn't go up any further. It always increases by a little bit every time. Lastly, I want to think about the domain. The domain is quite clear here. It is definitely not going to take on any values that are negative. The reason why is this. Can you tell me what number I have to raise 10 to give me negative 5? Or sorry, negative 10. And no, it's not negative 1. Exactly, it doesn't exist. You can see this just by looking at the exponential graph, right? A generic exponential graph will never dip into the negative zone. And remember, this question graphically asks, when does the function 10 to the x cross the line y equals negative 10? As we see, just obviously, it doesn't. It never does. Therefore, there is no answer for x. No answer for x. at least no real answer, but that's for another day. That clearly tells us that logarithms, logs, do not accept negative inputs. So it's similar in that sense to square root function. Okay, big problem here. One more warning that I would like to administer is that you cannot have b being a negative number. Okay, so let me just write that down. Oops. B cannot be negative. Why? Think about it for yourself. Suppose b were negative. Then we can write log of negative b, I guess. X is equal to something, right? And what would this look like? Okay. Let's just evaluate it for a couple of numbers. Let's try negative b. What number do I have to raise it to in order to get b? Well, that's a bit of an issue, because 1 doesn't work, negative 1 doesn't work, so this thing will never assume the value of b. Okay, alright. What about b squared? Aha, that one's easy, right? Because negative b to the power of 2 is equal to b squared. So here we do get a number, but as you can see, every time I multiply, every time I raise the exponent here, it's going to alternate. Just write that down here. Every time I raise this here, it's going to alternate between a positive number and a negative number. So this will be a negative number. If I put a 4, it'll be a positive number. Now it's a negative number, and it's just horrible, right? It's the same reason why when you have exponential functions, b here is never a negative number. Okay, hopefully you've noticed that. But for the exact same reason, b here can never be a negative number. Okay? Those are the main points about logarithms and evaluating them. So in terms of new material, we're done for today, but I just want to spend the rest of the time going through a couple of simple examples that just apply everything that we've learned here today. So they're going to be mostly evaluation problems. Hopefully that's not too difficult. So the first one that we have is log base 2 of x squared plus log 2xy plus log, minus plus log base 2 of y squared. And the question is simply to simplify this to a single log expression. Okay, so just simplify this, try it on your own. Okay, so the first thing that you should notice is that we can use our logarithm law to pull out the 2 and pull out the 2 in the y squared and the x squared, right? So let's just do that quickly. Alright. Maybe another thing that you notice is that we can use our multiplication rule here. So log 2 times xy is the same thing as log 2 of x plus log 2 of y. Okay. Then all I'm going to do is distribute the negative sign. So again, I put the brackets there to be super careful. And then it should be pretty obvious now what to do. So minus log 2y plus 2 log 2y is going to be log 2y. Voice crack. And then we're going to get a log 2x here similarly. And then finally we can finish it off just by using our log laws. Log 2 of xy. Okay? So a pretty easy simplification. The key points are to just simplify whenever you see exponents or multiplications. Next, here's a little more tricky one. Maybe erase this. So same idea, simplify to a single expression involving log. We have 1 quarter log x squared minus 1 to the 4 minus 1 half. Oops. Oh, that's confusing. Okay, minus 1 half log x plus 1 squared. Okay, so hopefully the first things that you see are that we can use our exponent rule. We can bring down the 2 and we can bring down the 4, and then that kills the 1 half and it kills the 1 quarter. So that's a first really nice simplification that we get. Next, we are going to use our subtraction rule. Now remember, just because they're added inside the log doesn't mean that you can separate it out. Remember, the rule is log base b of a, or alpha, plus log base b of beta is equal to log base b of alpha beta. It's not the other way around. You can't have alpha plus beta in here or alpha minus beta in there. It doesn't work like that. This is the only rule that you're allowed to use when you're doing addition and multiplication things. We do have a rule though which does say that log base b of alpha minus log base b of beta is equal to log base b of alpha over beta. So we're allowed to use that, and that's what we're going to do here. So just applying that directly to this, you get a log of x squared minus 1 over x plus 1. Hopefully you can see the factorization there. X minus 1, x plus 1, all of that over x plus 1. And clearly the x plus 1's factor out. So then you're just left with log of x minus 1. Okay? Next, we're going to go back to some more evaluation style questions with numbers in them. So here we are. We've got 5, the log base 5 of 25. Trying to figure that on your own. This one's quite easy. You can just look at this top thing and see that it is equal to 2 because 5 to the 2 is equal to 25. Remember, the answer is the exponent. Okay. Then that just gives us 25 here. Okay. So because you get 5 to the 2, and that gives you 25. Next, here we have log, a little trickier one, base 5 of 3 root 325 minus log base 3 of root 27. Okay. Now I want you to think about this one. It's a little trickier. So log base 5 of this thing, we want to write it really in terms of 5 to the something, right? So we have to think 5 to the what gives me 3 root 25. The first thing I want you to notice is that the cube root is the same thing as raising to the 1/3 power. And the second thing I want you to notice is that 25 is 5 squared. Again, brackets for security. Then this gives you 5 to the 2 over 3 by our multiplication by exponents rule. Okay? So the number that goes in here is 2/3. Therefore, this whole number here is just 2 over 3. Next, for this one, we are asking ourselves, what number do I have to raise 3 to in order to get root 27? Again, the first thing that I want you to think about is first to turn it into an exponent, and then notice that 27 is 3 cubed. Then, by the same law that we used there, we get 3 to the 3 over 2. And therefore the box here is 3 over 2. Okay. Notice that you could not use the subtraction by logarithms law because the bases are not the same. 5 is not the same as 3. So you cannot use it there. But in any case, this gives you 2 over 3 minus 3 over 2. And that you can solve just by doing an operation on just with subtracting fractions. I'm not going to waste time doing that here. Excellent. One more thing that will just segue into what we're doing next week is just solving an equation using this log stuff. So, for example, let's say I have 2 log x minus 2, and this is log x minus 2 equals log 4. Okay. And these, remember, without the subscripts, it means base 10. So what we're going to do is simply just use our laws of logarithms in order to evaluate this. Right? Let's see here. Okay. So first up, what we're going to do is we're going to rearrange so that all the log expressions are on one side. We're going to get 2 log x minus log 4 equals 2. Pretty easy. Then we are trying to solve for x, right? So what we're going to do is we're going to bring this 2 inside the expression using our exponent rule. So log x squared minus log 4. And then notice that both sides have that the base is 10. Therefore, we can combine them together. So we get log x squared over 4 equals 2. Okay. Now I want you to see if you can finish it off from there. So remember, what this expression is saying is 10 to the 2 is equal to x squared over 4. That's just translating it into an exponential form. Then we can solve this quite easily as follows. Okay, so we get plus or minus 20. The only issue here is that every time, I'll put this up here as a very important piece of wisdom, every time you solve a logarithm equation, plug your answers back in. Okay, that is it's horrible. I don't know why it's doing that. Maybe I'll rewrite it in blue because this marker is just horrible. But basically, the key point is to plug your answers back in. Plug answers back in. Super, super important. If you forget to do this, you'll make really big mistakes. As follows. Look. So if I plug in plus 20, there's nothing wrong with that. But let's say I plug in negative 20. We get 2 log negative 20 minus 2 equals log 4. Okay, can you see the problem with this? I hope you realize, because of our discussion earlier, that this does not make any sense. You cannot take the logarithm of a negative number. Therefore, the answer negative 20 is inadmissible. Negative 20 inadmissible. Therefore, x can only be equal to 20. Right? So that's one example of a log equation that involves a variable. Okay? So as you can see, it's pretty much just boiling it down. It's doing the same thing that we were doing earlier, just boiling it down to a single log expression, and then solving just using the definitions of logarithm. Okay? So really nothing too hairy. Maybe you would like to try one more on your own. So here's another one. I'm pulling these from tests, by the way. So this is really end-level log equation stuff. It's not horribly difficult. All right. So this one's a little tricky. Log base, 3 log x minus log 3 equals to 2 log 3. Now this one here is just ready to set you up for some mistakes. So let's go ahead and take this slowly. The first thing that you want to do is bring all the log stuff to one side. So let's go ahead and do that. We have 3 log x minus log 3 minus 2 log 3. Maybe that's something that you should note for yourself. Bring all logs to one side. That usually helps. Okay, that will usually help. The next thing that you want to do, is to simplify this. So this becomes negative 3 log 3, and you get this. Then use your exponent rules. So you get log x cubed minus log 3 cubed, which is 27, equals 0. And then just all you have to do is use your division law. So you get log x cubed over 27 equals 0. Okay. And now the question becomes, if you translate it, it becomes x cubed over, becomes 10 to the 0 is equal to x cubed over 27. That's just translating, because remember the answer is the exponent. Okay. Then this is of course 1, and then systematically solving, you get that x must be equal to 3. And this does work if you plug it in here, you get no issues. The only issue is that log can never take a negative number. Can never take in a negative number. All right? Okay, so those were a couple of tricky and moderately difficult examples. Next lecture, we're going to be going through some more examples. And the log equations can get really quite tricky, and we're going to see how they can be used actually to solve the more elusive problem of exponential equations. So next lecture is going to be the last lecture for advanced functions. We're just going to finish off with some graphing, some more of these log equations, and their connections to exponential equations.